Hi there. This is the third video on covering second law in fiction. I'm going to do these last two questions together. All right. So we have a classmate resting on a level tile floor, and there's a force being applied to that person. So normal force, floor on person, earth on person, force applied. I don't know, classmate. Yeah, who knows? I wish I call it just push on person. That's equal to 100 newtons. And it says there's kinetic friction, so this person's moving, and there's friction. So floor on person. And just a note here that this person's not accelerating up and down, so vertically it's balanced, and Fn equals Fg. And we can even calculate that right now. That's mg, which is 50 kilograms times 9.8 meters per second squared. So just under like 49 or something, 490. Okay, and then horizontally, it's accelerating, and Fa is greater than force of friction. All right. He wants to know the acceleration of the classmate. So F net is equal to Fa minus force of friction. Force of friction is mu Fn, which is 0.15 times 490 newtons. Oops. 73.5 newtons. So we have F net is equal to 100 newtons minus 73.5. I should do that in my head. 26.5. Okay, so that's the total force acting on that person, and then it's asking for the acceleration. So acceleration is F net divided by mass. So the person was 50 kilograms. Oops. 0.53 meters per second squared. Okay, so it's a bit of work, but should be pretty straightforward. Again, the only equations we're using this whole time are F net. Sorry, the only formulas that a person's given that we're using here is F net is equal to mass times acceleration, force of friction is equal to Fn. And I guess we're also using Fg equals mg. This though comes from the free body diagram. It's not something you get put on a formula sheet. Okay, question C then. If the classmate was resting on carpet, so there's a higher coefficient of static friction, does that person accelerate? So I guess the question is, does F is force applied greater than force of friction? If it is, then the person will start to move. If it's not, if force of friction is greater, then the person will actually never move. So force of friction is equal to mu s times Fn. So that's 0.25 times 490 newtons. That's just divided by a quarter. So it's over 4. Yeah, oops. It's going to be, I got something wrong there. 490. Oh, times 0.5, sorry. Okay, so that's 122.5 newtons, which is greater than 100 newtons. So no, does not move. Alright, last question, number 4. Draw a force diagram of the block, so this guy here. So there's a force push here that's equal to 15 newtons. And it's on a surface, so that means there must be a normal force acting in the other direction. It's not accelerating to the left or the right, so that means it's balanced. That has to be 15 newtons. I know there's gravity acting on it. And that gravity is, or that force of gravity is 0.5 kilograms times 9.8 meters per second squared. So that's 4.9 newtons. So the question is there any friction happening here? And yet it tells us friction is keeping the book from sliding down the wall, and we can kind of look at a free body diagram. If that was the case, there would be a net force acting down and the book would be sliding down, but there isn't. There's friction. Because it's not accelerating up or down, the friction must be the same as the gravitational force. So there's our free body diagram. So what's the minimum force and coefficient of friction required to keep the book from sliding? Well, the minimum force is the friction force equal to 4.9 newtons, and the coefficient of friction is, so mu is Fn divided by, force of friction divided by Fn. Fn is 15, so this is 4.9 newtons divided by 15 newtons. So it's the static coefficient of friction of 0.33. And that's it.